Okay, so how many of you, how many of y'all have ever heard of an invertible ideal? So, mixed bag a little bit. Well, so we talked about valuation domains, and again, it probably appears like I've done with my little patented segues into something obscure. However, this is again kind of related. So I want to talk today about we've seen examples of this so far, but I probably didn't underscore that. First, let me get this definition here. So here we have R as an integral domain. Okay. First thing I'm going to do is find something called fractal ideal. Notice I said fractional ideal of R and not contained in R, because fractional ideals aren't necessarily contained in R. Is a, let's see, no. R module. Okay. So when I say fractional ideal, I mean a submodule of quotient field R. And not just any submodule. I need some kind of finiteness condition, and my finite condition is this. Such that there exists a non-zero A and R, such that A I is contained in R. This is a finiteness condition, right? Because what is I? Well, it is closed under addition, and everything's inside of K. So everything in I can be written as fractions, A over B, where both A and B are in R, right? And this is a finiteness condition right here. So it's closed under addition. It's an R submodule. So when you hit any of these fractions, something in R is still in this I, right? And there's a master A, not zero, that knocks everything down into R. So what this means is sort of everything in I has a common denominator. Of A. That is to say, if X is in I, then X is now. This does not mean that this is just everything in R divided by some particular A. It could be smaller than this, right? So let me give you an example. Let's let R be Z. K is rational numbers. Q is not a fractional Z ideal. It's not a fractional ideal C, right? Because there is no universal non-zero element of the integers that knocks everything Q down into Z, right? Whatever it is, say that your universal thing is A, all I have to do is look at 1 over 2A and it won't work anymore. But okay with that. But let me give you some examples of things that are. Notice This is everything that can be written as n over 2, where n is an integer. This is easy to be seen, a submodule of Q, and of course, if you hit this thing with 2 or 4 or 8 or 6, any of these, it blasts it back down. Everybody do it? Yes.
The ideal.
That's right. Not a fractional ideal of C or not a fractional C.
All right.
Two-thirds C. So this 0, 2/3, 4/3, 2, 8/3. I'm gonna start messing that up. But anyway, this is certainly a fractional Z ideal, right? And the smallest thing that I can think of that you hit this is multiply this by 3 and it's in there. Notice, and this is strictly contained in 1/3 Z, and that's what I mean by this thing always is. Right, notice. Any ordinary ideal of R is a fraction.
Yeah, I think I got confused now. I understand why. This is a stupid name.
What's that?
Because is it an ideal or is it a module? Or is it?
It is a module, but this is the terminology they use. They call it fractional ideal. Right, but it is not contained in the ring in general.
So yeah.
Right, it is really a module,
Okay.
right? So notice any ordinary ideal, one that is contained in the ring, is automatically a fractional ideal, because all you have to do is take A through 1. Right? So, so think of it this way. An ideal itself, an ordinary ideal. So what you're used to, what is confusing about this? So what bothered me the first time I ever saw something like this is, this doesn't seem like an ideal, does it? Because 1/2 is in here, right? Well, 1/2 times 1/2 is not in. Right, so this thing is not necessarily close under multiplication, but that's okay, because think of an ideal this way. Think of an ideal just as an R module. You take something in the ideal, you hit it with something in R, and it's still in the ideal, right? Now, if the ideal is contained in the ring, you sort of get the bonus, something in the ideal times something in the ideals in the ring. But maybe in general, this is a generalization of this.
Got it.
Right.
All right, thanks for that.
Okay. Other questions? So, of course, fractional ideals, they contain all the ordinary ideals. But of course, there are some like this. Let me give you another kind of general example. Okay, so take any integral domain you want and take any non-zero element quotient field. KR is a fractional ideal. Right? Because, let me prove this for you. Certainly this is a submodule, because if you take KR1 plus KR2, it's K times R1 plus R2, right? And when I multiply this by anything in R, it's still in KR, right? So no problem there. What's my magic number here? Well, notice that since K is in the quotient field, K is equal to B over A, some BA in R and A non-zero. Right. So KR equals B over A R. So A times KR is equal to BR, which is contained in R. So in other words, so here's the moral of this story. Any principal ideal that is principal in a more general sense, when I multiply it by an element of the quotient field, is fraction. So a fractional ideal is just a submodule of the quotient field where you can kind of collect the denominators in a certain sense. Now, let's go say invertible ideals. What is an invertible ideal? It is a very, very nicely behaved fractional ideal. Yes,
Do you want to say any principal ideal is invertible?
it is, but I'm not there
That's
yet.
not- okay.
Yeah, that's right. That will be true as well. Yes.
Why did you write the, we already have any ideal that's actually?
When I say principal here, let me clarify. This is the form K times R, where K is in K. Right, it can be any element of the quotient field, not just, so for example, not just Z, but 1/2 Z, which is not an ordinary ideal.
Got ahead of myself. I was just forgetting that.
Yes.
So you can take like a finitely generated R submodule K, and you'll get the same, you just take the product of the denominator.
Yeah, that's right. You could do that. Yes, certainly. So that would be another kind of class that fits in there if you took all the finitely generated R submodules. So yes.
Sorry, I'm a little bit confused. You have any principal ideal, but ideals are necessarily contained in R, and that's not. I'm confused why you're calling that principal ideal.
Principal fractional ideal.
Okay.
So what does it mean to be inverted? Well, let me first define, sounds a little strange, but the first thing I'm gonna do is define the inverse of an ideal. Definition. If R is a domain, then I is a non-zero fractional ideal. And I is a fractional ideal. Then we define what's called the inverse. This is everything in the quotient field that dumps I back into R. So we make this definition here. This is just a collection of elements. But I'm gonna make some observations about this. By definition, I inverse. Well, when you multiply anything in I times anything in I inverse, you end up in R. So this is always a subset of R. Always, by the way we've set this up. If I inverse equals R, we say I is inverted. So let's look at this. Let me first make an observation here. Notice that I inverse is also an R submodule. Okay. Because if A and B are in I inverse, then AI and BI are both contained in R. Right? Therefore, AI plus BI, and of course, the sum of two sets that are contained in R is still contained in R. Right? And also, for all R and R, RAI is contained in R. Therefore, RA is in I inverse. Right, okay. So these are two R modules that you're multiplying together, and you know, of course, in general, this is a sum of things that look like AB, where A is in I and B is in I inverse. Let me give you a large class module or of ideals that are invertible. The principal ideals in our more general setting. So here's an example. Domain and K is quotient field. And so suppose we have this situation here. Now, this is our sort of general principal ideal. But I be K times R, so it's principal in this more general sense. Anybody want to guess what the inverse of this is?
A inverse R.
How about that? Notice that anything of this form here, when you hit something in this form here, it's certainly an R.
Do you mean 0 is not equals to K in K?
I do, thank you. Yes. This would be rather boring if I'm doing this whole example about zero, isn't it? Yes, yes. Of course, it's easy to check that everything here is an I inverse. And of course, you can kind of backbeat it and see that everything in I inverse has to be in this form. And notice that I inverse is K inverse R, which is R times R, which is R, since R has an identity. So this is a big giant class of ideals for any integral domain that are always invertible. It's the principles. Now, here's the big question today, right? I mean, this is a really stupid definition that I've been building up for 20 minutes of class time today. If this is equivalent to principal ideals, right? I mean, why in the world would I bother to do anything? Examples are always very important. Here's the question. Is there such thing as an invertible ideal that's not principal? Lots of nods out there. Anybody know one?
And you're gonna be joining like invertible two.
So here's kind of the best example I can think that there are other, obviously, other examples all over the place, but so let's go through this. I'm gonna actually come kind of roundabout on this and show you that this idea is invertible. Let's let R. I think I went through this exercise once a little bit, but I'm gonna actually show you. Do y'all remember when we looked at this ideal here? Let's look P equal. And then I had P bar is the conjugate ideal. I don't know if y'all remember back in the day, but we did the following computation. Now, this thing can be generated by up to 4 generators, right? Let's see. Generated by 9, 3 plus 3 radical negative 5, 3 minus 3 radical negative 5, and the product of these two, which is 6. Right?
9.
Said nine out loud.
I said 9 out loud too. I need to stop drinking stuff out of aluminum cans. All right, so there, that's better, right? Let me point out that that is certainly true, right? I mean, everything in here is right. The interesting thing is you actually get this. Because for this containment to hold, really what you need is you need a 3 to be in here somehow, some way. But it is because this minus this is 3, right? So you get an equality here. So what I have, what does this allow me to do? This allows me to build following figures. So I have P now. And so this is actually the ideal. This is essentially. That's P inverse right there. Because notice that this thing throws everything in here back into R, right? When I multiply, right, when I have anything for P inverse, right? So like 1 times this, well, that's clearly back in R, so I did this already. When I multiply this generated by 3, I get 1 minus radical negative 5, which is in R. And when I multiply this generated by this, I get 6 over 3, which is 2, right? And I get the extra bonus. Of course, P inverse times P is contained in R, and I also get the equality by our observation. So in this case, we have seen already that P is not principal. And if you remember the argument earlier, I'll briefly go over it. This thing in this ring has norm 9 and this has norm 6. So if there were a principal generator, then it would have to have a norm that divides the greatest common divisor of 9 and 6, which is 3, right? There is nothing in here of norm 3. There's certainly something in here of norm 1, but if this had a norm 1 generator, this would have to be a proper, it can't be a proper ideal. So this is actually not principal. So this is an example. So this is not all for naught, because there are ideals that are not principal, and yet they're invertible. let me, first. Definition. 2, 3. We define the class group bar. Now I'm gonna step back a little bit and talk a little bit about this. INVR is the binomials. And this is invertible ideals of R, but remember, not necessarily contained in R. And print R is the group, again, abelian principal ideals. So let me kind of take you through this here. Note. Suppose I and J are invertible ideals R, right? So these are submodules of the quotient field, and they have this invertibility problem. What can you say about IJ? It is also invertible. Notice IJ inverse equals I inverse J inverse. This is easily verifiable. I love commutative algebra, right? Because notice I'm very flippant with the order here. This is J inverse, I inverse, which is I inverse. Of course, this is the module generated by 1. This is 3 modules, so over R. So in particular, the collection of invertible ideals forms a group, an abelian group, to be sure. The inverse of I is I inverse. So what do you suspect the identity is? With identity R, the ideal generated by 1. Because R times any ideal I, whether it's a fractional ideal, is still I. Okay with it? Now, the invertible ideals are, in a certain sense, too big, right? The big, messy, right? Let me give you an example of Z. Every ideal in Z is invertible. Can anybody tell me why? there's a important principle here. We need to. That is correct. Every ideal Z is a principal ideal, and so every ideal is a verb, right? Lots of noise in this, right? A principal ideal for every stupid integer that you can come up with the exception of 0, right? This is a set of principal fractional ideals. This is also a very good. So I can write this down a little bit more coherently, if you will. Principal ideals of R consists of this, where K runs through the non-zero elements of the quotient field. We've seen in an earlier example that every one of these suckers is an invertible ideal, right? So this actually forms a subgroup of all the invertible ideals. And this is called the class group. Whenever you have a subgroup, you can always take a quotient. This kind of squeezes out the noise, right? So for example, if you take the ordinary integers, the class group is trivial because every ideal is principal, right? The invertible ideals are essentially every fractional ideal that you can think of, other than 0, modulo the principal ideals, you get the trivial group. We will see later for certain types of domains that the class group basically measures how far away from being a UFD you are. If you have, for example, a ring of algebraic integers, bigger the class group, the messier things can be, right? So let me just kind of point this out here. So here's a little proposition. R, if R is a PID, then CLR is true. In the sense that it's PID. It suffices to show that every fractional ideal R principal. Okay, listen, folks. I know with all kinds of confidence that every ordinary ideal of R is principal, because after all, it's a PID. But what about a more general fractional ideal? How are we gonna,
Send it into R and get an ideal.
that is correct. Let I be a fractional ideal. Notice that there exists a non-zero A in R such that AI is contained in R. And what does this mean? This means that means that AI is some X of R, because I know that R is principal ideal domain, so it's generated by some element X and R, correct? So I now claim and this is clear that if AI equals XR, then I equals X for AR, is that okay? All right. So is principal. So the class group is trivial. But here is, here's another theorem. This is one of my favorite theorems. All time, maybe. We're gonna come back to the class group, and in fact, we're gonna beat it to death, rings, algebraic integers and so forth. Do some computations there. Use it for elasticity. Right after we. Well, this is a little bit more. Here's a theorem. 724. If R is a domain and I is an invertible ideal, R, then I is finite. Let me make a couple of remarks. I think this is a wonderful theorem because this is not obvious by any stretch of the imagination. I don't think. Unless somebody, maybe one of you sees something that I don't, but I mean, just because it's invertible, I times I inverse is equal to R. It's not clear why that ideal would have to be finitely generated. So that's one of the things that makes this interesting. Another remark that is important to make, I think, about this theorem is the converse is wildly untrue. Right? Just because you've got a finitely generated ideal, if that sucker ain't principal, in fact, it's probably not invertible, right? Invertibles are actually pretty scarce. They're more general than principals, but they're pretty rare. And in fact, being invertible is also, it means it's projective R module. So that's kind of, so very close to being free in a certain sense. So why is this true? Well,
Close to being.
yes, right, because in a certain sense, projectives are almost free because they're the direct sum and free. If you were to argue with me about it, I probably can't argue back. Because your tomato is my tomato. I mean, somebody's close to somebody else's far, right?
I mean, I was just trying to understand.
Yeah, well, in that sense, what I mean by that is, at least in classes of rings that I often work with, projectives and frees are pretty close because frees are the nicest. They're direct sums of copies of the ring, and projectives are direct sums of those. So we know, what do we know? Very little. I inverse is equal to R, right? And let's try to capture what this means, right? This means that one is an I inverse, right? And really, that's all you need for this thing to be invertible, right? Because by construction, I inverse is contained in R. So this is going to be actually an ideal. In general, this is going to be an ideal inside of R because it's contained in R. And so how do you tell that ideals in R are the whole thing? Well, it's if and only if they contain the one. So this is the linchpin, right? Well, so what does it mean for one to be I inverse? It doesn't mean that one is something in here times something in here. It means it's a sum of those things. So one is equal to A1 B1 plus A2 B2 plus AK BK, where AIs are in I and BIs are in I inverse. Right, so I can express one as a linear combination. Each of these things are something in I, something in I inverse, right? Okay, now what? I'm gonna make a crazy claim. Because it's the only way I can get my proofs to move forward. And my crazy claim is I claim that I is generated by these elements, right? That's my point. Now, what is clear is this. Um, right, as an R module, if you will, it's clear that I is generated by those things, or I'm sorry, that what is generated by those things is contained in I, correct? Right, because any R linear combination, these things, since they're all in I, must be inside I, right? Question is, why is this enough?
By your equation there by adding an M to I.
Okay, so good. For other containment, let X be an I and multiply start equation, this one, multiply this guy by X. And what do I get? I get X is A1. So I'm gonna write this grammatically. Everybody okay with that? And notice that as each BI is in I inverse and X is in I, then BIX is in R. Right, because that's what I inverse does, is it flings this element X and I back into R. And so X is an R linear combination of A1 up to AK. Therefore, we get the other containment we need. Complete response. And in fact, I love this. This is what's one of the great things about doing mathematical proofs. It actually told me something that I didn't write down. As I can, what else does this proof tell me?
Gives you generators, like.
Right. The least number of generators I need for I is actually the smallest relation that I can find that looks like this, right? And what does it say about the number of generators by inverse? The minimal relation should also equal that as well. So the number of generators by an I inverse are the same, or well, the minimal number, I should say. So that's two cool things that we got out of it. Okay, any questions?
So just to clarify, in the sense of finitely generated, we're saying it's finitely, it's R model. Right?
That is correct. Right. Here, 6. I'm gonna stay with this one. Whoops. If R is semi-quasi-local, and I is an invertible ideal of R, then I okay, this is kind of nice, and this will be useful later. By the way, so anybody Anybody in band and high school, anybody know what a Hemi Demi semi-quaver is?
You should say.
Ding, 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 oh, you win the prize today, yes.
You should say that, talk, about modular forms and how there's like weak, almost.
Oh, yeah.
Blah, 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 so it's weak, mock, weak, almost, blah, 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 whatever, for.
Math is always bad about that, so we put all these kind of adjectives here, and in computed algebra, we make it worse by just turning it into abbreviations, so, yeah. Semi-quasi-local, anybody remember what that is?
Finitely maximum ideal is not necessarily necessary.
That's right, it's, yeah, the quasi means it's not necessarily, the ideals are not necessarily finitely generated, but, the important thing here is this is just an integral domain that has only finitely many maximal ideals. So if you've got finitely many maximal ideals and you have an invertible ideal of that domain, it's got to be principal. This is actually very important and allows us to develop some stuff.
I was wondering how weak you needed to be to be principal back. You see?
Oh, right. Yeah. So let's see how quickly I can do this here. I'm gonna. So I am going to do the proof, assuming it's got only one maximal ideal. See if you can figure out how to expand this to finitely many. So suppose R is quasi-local. Unique maximal ideal. And I is invertible. And without loss of generality, we'll say that I is contained in R. Right? And let me tell you what I mean by without loss of generality. If it's invertible, it's a fractional ideal, so there's some non-zero thing that will push it back down to the ring. I'll assume I've done the pushing. It's already back down in the ring, and it won't make any difference to the proof here. Let's say that I we already know from the previous result that I must be finitely generated, and I inverse is equal to R. So we must have A1 B1 plus AN BN equals 1 for BI and I inverse. So this is so far it's looking very much like what we did before. Now, here's the trick. Each AI BI is in I inverse, which is in R. Right, so each one of these terms, actually AI BI is in R. So if M is maximal ideal of R, then without loss of generality, A1 B1 is not in M. That's the cool thing about local. Because if every single one of these terms is in the maximal ideal, that means one's in the maximal ideal. So at least one of them has to be outside the maximal ideal. And therefore, A1, B1 is a unit in R. See, that's the key. You're not in the maximal ideal, you're a unit. You have to select things a little bit more carefully in the semi-quasi-local case. And so what we get is every AK is equal to U inverse UAK. Which equals U inverse A1 B1 AK. And therefore AK. Notice that, of course, right. This thing is in R, so, or I'm sorry, this thing is R, B1 AK, therefore, AK is in the ideal generated by A1. So, so that wraps that up. See if you can generalize that to, what the shortcut here is, you know that if it's outside the maximal ideal, it's a unit. If there's more than one maximal ideal, you got to play around with it, but it's essentially. Any questions on that? Yes.
Why do you say without loss of generality, without loss of generality, I is important?
Because if it's not, I will just multiply I by some appropriate non-zero element and push it down into R. And so I can multiply, if I is not in R, then I can multiply it by some element X. Now Xi is in R. And what this proof shows is Xi is principal. Therefore, the original I had. Okay, other questions? Okay, well, I will see you folks on Wednesday. Oh, don't forget about my office hours today. I've got another one of those lovely meetings at 1, but I will be in my office until then.